Hello, students. Welcome to the 39th lecture on particle physics. And in the last two lectures, we were discussing about neutrino oscillation and neutrino mixing. What I had told you that in general, in an accelerator experiment, one has proton beam that strikes the target to have pions, and these pions then decay to give neutrinos. Now, simply speaking, what we are talking about that a pion is giving rise to W boson, and that is giving us a muon and a neutrino, and this neutrino is traveling and is getting detected. Now, two concepts we talked about. One was the short baseline experiments and long baseline experiments. The other was a near detector and a far detector. What we talked about that in general to have a good control on neutrino flux and detector calibration, we put a near detector and then another detector at far distance of say 300 kilometers or 700 kilometers or something like that. Now, the important point is that what is happening, a W boson is giving rise to a neutrino and a lepton, and this W boson can, if it is giving rise to a say muon type neutrino, then this muon type neutrino is traveling and it is getting detected just at a short distance. The detector is placed, detected at the detector via the observation of the charged lepton. Therefore, the basic reaction that we spoke about was that a neutrino of say some flavor L is interacting with the neutron target, and we have a charged lepton and a proton in the final state. And these leptons are getting detected. Now, the important point is that in at short distance, we don't have oscillation, and therefore a nu alpha remains a nu alpha. While when we increase this distance, the far detector is placed at a distance of say 300 kilometers or 3000 kilometers depending upon the energy. Then what is happening, this nu alpha of one flavor is changing to nu beta, and then this we are detecting, just for example, a beta minus. This beta minus can be, say, if this is mu, then this can be E minus. That means a nu E has interacted with the neutron target and we have an electron in the final state. And this is the oscillation. Nu mu is changing to nu E and we are detecting electrons. That means this is an appearance experiment where in the initial stage electron type neutrino was not there, and now we are finding out electrons in the final state, and that means these electrons have been produced through the interaction of nu E with the target material. And this is appearance experiment. And the disappearance one is that we are detecting at the far detector muon itself. The detector is sensitive to detect muons. Then we will see that how many nu mu's have got disappeared. That will be disappearance experiment. Therefore, in general, we have the source, and that source we can typically represent it by a W boson, which is giving rise to a lepton and a neutrino, and this neutrino is traveling, neutrino of say flavor alpha. This is traveling, this neutrino is of flavor alpha, and this neutrino is traveling, interacting with the neutron target and giving us a charged lepton of flavor alpha. That means muon type neutrino will give me a charged muon in the final state. This is at the near detector site. Now, the other important point that we are discussing, that when we are talking about long journey, then in the long journey a nu alpha is changing to nu beta, and that is why what we are exactly observing is a lepton which is of different flavor than what we had observed in the near detector. And this is what we are saying, that if say W plus is giving us mu plus and nu mu, then this nu mu is traveling, and then we are observing here an electron. Therefore, this is basically representing, this W plus is giving us mu plus and nu mu, and then this nu mu is getting changed to nu e, and we are observing an electron in the final state. That is why here in the second figure, we are showing that nu alpha is changing to nu beta. Now, what we are saying, that actually neutrino flavor states and the detection that takes place, the detection is also of the neutrino flavor, and we have a charged lepton. But when they propagate as mass eigenstates nu1, nu2, nu3 in the three flavor scenario. And in the last lecture, we took the example of two flavors that we will discuss very shortly. And what we are saying, that a nu e is basically some admixture of nu1 and nu2 and nu3. That is what we are representing it by A, B and C. They are some admixture component of 1, some other component of 2, and some third component of 3. Similarly for nu tau and nu mu. And in other words, you can say that we have these flavors here of different colors, and what we have here is a mixture of states, and these are the mass eigenstates, and they are having the different composition of nu mu. Therefore, the important point was that we started with a certain flavor, and then we are saying that probability of surviving that flavor after covering a distance L is not 1. It has got reduced, and that reduction has got into the production of another neutrino. Therefore, we started with a unitary matrix with this theta as the mixing angle, with the mixing between the different flavors, and this nu mu nu e is expressed in terms of nu1 and nu2 mass eigenstates. Then we said that the evolution is taking place following the quantum mechanics, because neutrino oscillation is purely a quantum mechanical phenomena. This is nu1t is nu1 0 e to power minus ie1t. Then we said that, okay, to start with at time t equal to 0, we had only nu mu's. We don't had any nu e. Therefore, at time t equal to 0, we had only nu mu's. Therefore, if we do the inverse transformation, that means we write neutrino mass eigenstates in terms of the neutrino flavor states, then we are writing it as instead of this u, we will have a u dagger, and yesterday we saw that this is nothing but cos theta minus sin theta cos theta, and we are writing nu1 in terms of nu mu and nu e, and nu2 in terms of also nu mu and nu e. Now, to start with, what we are saying, that at time t is equal to 0, we don't had electron type neutrino, for example. We had only muon type neutrinos. Therefore, we wrote nu1 0 as nu mu 0 cosine theta, and nu2 0 as nu mu 0 sine theta. As you can notice that this component will be 0, because there is no nu e at time t equal to 0. That means at the starting point where we have nu mu production, where W plus is giving us mu plus and nu mu. This nu mu we are talking about. All the time we had only nu mu. This probability was 1, and probability of nu e was 0. This is what we are talking about. And then we wrote this nu1t as nu mu 0 cos theta e power minus ia1t, just putting this here. And then we obtained the amplitude of muon type neutrino at time t equal to t upon time t equal to 0. This was cos square theta e power minus ie1t plus sin square theta e power minus ie2t. Once we have this, then we got the intensity, and intensity was the square of the amplitude, and this we solved, and we found that this is 1 minus sin square 2 theta times sine square delta m square t by 4e. This is the formula for nu mu that remains nu mu. And therefore, as you can notice, if the mixing angle is non-zero, this probability is not 1. If there is a delta m square which is finite, then this will not be equal to 1. That means for the oscillation to happen, we must have a mixing between the different states, and then delta m square also we require to be non-zero, and that means one of the mass eigenstate that we talked about, this should be non-zero. One has to be non-zero. Okay, and then we are getting this value. Now this value which we are writing, we have assumed to start with natural units. That means c is equal to h cross is equal to 1. If we stick to all c and h cross, then we can write this expression as delta m square c4 L by 4e h cross c. And from where we are getting this L and C? Because we are replacing this time. Speed is distance upon time, and neutrinos are extremely relativistic particles, and that means energy is almost equal to the momentum of the particle. Again, we are writing E equal to P, assuming that C is equal to 1, the natural unit. But if we stick to with the C and H cross, we will have this factor delta m square C4 L 4E H cross C. This H cross C, if you remember, this is 197.33 MeV Fermi, and 1 Fermi is 10 power minus 15 meters. This L is in meters, this E is say in GeV, and delta MC square whole square, that means this we are writing, this is the mass difference. That means mass difference will be in electron volts, this will be electron volt square. Therefore, if we stick to that we stick to the with C and H cross, therefore the in the parenthesis the term which we are writing as delta m square t by 4e. For example, if we just stick with C is equal to 1, then instead of t we can write L only. But since we are talking about C and H cross, to see that what will be its unit, this should be a dimensionless quantity. Therefore, we are finding that actually this value is delta m square C4 times the length which the neutrino has traveled times the energy divided by the energy that the neutrino had, and this H cross C. And H cross C is 197 or roughly you can say that this is 200 MeV Fermi. And this Fermi is 10 power minus 15 meters. Therefore, if you stick to this, then the expression that we get is 1.27 delta m square ev square L kilometers upon E in GeV. Therefore, this is the general expression that you will find in the books. And see here, this is here 1 minus part is gone, because this the other half part that we talked about, this part, this is 1 minus this thing. That means this is for two flavor oscillation, this is the part where nu mu has gone to nu e. And that means if you notice, this is nothing but nu mu to nu mu plus nu mu to nu e. This guy should be equal to 1, because you have to conserve the total neutrinos. And if you have three flavor oscillation, then it will be nu mu to nu tau to nu mu to nu mu, and nu mu to nu e. The sum should be equal to always 1. But here in the two flavor scenario that we are talking about, we have nu mu to nu e, the oscillation probability is this term. And if you talk about nu mu bar to nu e bar, you will have the same expression. If you talk about nu e to nu mu, you will have the same expression. Therefore, the important point is the probability of oscillation. If you say that Cp and Cpt both are conserved, then probability of oscillation of nu mu to nu e will be the same as the probability of oscillation of nu mu bar to nu e bar. And then if we talk about Cpt, then that means this should also be equal to Cp. Reverse this will be nu e bar to nu mu bar. This is what we have talked about. Therefore, the important point is that if we assume that Cp and Cpt both are conserved, then probability of oscillation of nu mu to nu e will be the same as nu e to nu mu. And that is why if we want to see Cp violation in the leptonic sector, either we will look at this or independently we will look at this guy. But if we want to see CPT violation, then in that case we will have to look for probability of nu mu getting converted to nu e to probability of nu e bar getting converted to nu mu bar, because Cp is giving us this, but then you have Cp is giving us nu mu to nu e. Cp will give us what? Nu mu bar to nu e bar, and then T will give us nu mu bar, nu e bar to nu. Therefore, this is the result of CPT. This is the result of CP, charge conjugation and parity. So, therefore, CP violation will be observed here and CPT will be observed by this. Therefore, people are also looking for this CPT violation. But the master expression for the oscillation probability, if we consider true flavor neutrinos, is given by this expression. And the important point is that for nu mu to nu e oscillation or nu e to nu mu oscillation or whatever you talk about, this delta m square has to be non-zero and theta has to be non-zero. Besides that, neutrinos have to travel some distance, and that means there should be a significant amount of L that we will talk about later in these two lectures, and we have certain energy of the neutrinos, and we will see that depending upon this energy our oscillation length will be decided. That means if say I am talking about 600 MeV of neutrinos at T2k, then this oscillation length to see the oscillation will be different. If we are talking about NOVA experiment at Fermilab, where the average energy of the neutrino is 2 JeV, then to see the oscillation, this L will be different. And this is what we will talk about in this lecture as well as in the next lecture. Therefore, the important point is this result that the oscillation probability for nu mu to nu e is given by this master expression. And if you want to see that how many muon type neutrinos have remained, that means you have to take 1 minus of that quantity. Now, what I am going to do, since we talked about two flavor neutrinos, I am making a general case for these two flavor neutrinos, defining the unitary matrix. We remember we started with cos theta, sin theta, and minus sin theta, cos theta, the general unitary matrix that we learned from graduation first year course. But here what I am going to do, I am going to take a general unitary matrix, and it will be true for all the flavors. And therefore, let us start with two flavor neutrino oscillation case, and that is why we are saying that a given flavor state is expressed as an orthonormal linear combination of mass eigenstates nu1 and nu2, and this is the unitary matrix. And unitary matrix means that U dagger will be equal to U inverse, and that this is my elements of the unitary matrices, and this is my U dagger, such that U dagger is giving us unity. Now, if you notice, this is the flavor state and this is the mass eigenstate. If I want to write mass eigenstate in terms of the flavor state, then you see nu j will be simply U alpha j star nu alpha. and this will be for anti-neutrino that we have discussed. Now this implies that u alpha j star, u alpha k, u alpha j, u alpha k star is delta jk, or u alpha j, u beta j star, which will be delta alpha beta. That will be the orthonormality property. And this is what we did by simply taking the matrix to be cos theta, sin theta, and minus sin theta, cosine theta. This means that the definite flavor state of neutrinos, that is nu e and nu mu, are composed exclusively of the mass eigenstates. The oscillation matrix is chosen to be unitary because in a scenario of two flavors in nature, where one flavor of neutrino is say nu e, oscillates to another flavor say nu mu, and vice versa, there should be no loss in total neutrino flux, implying that the total probability of oscillation is unity. This is what we have discussed, that whether you talk about nu mu to nu mu and nu mu to nu e, or if you say you have a beam where you are producing electron type neutrinos, then the probability of oscillation of nu e to nu mu and nu e that remains as nu e, this should also turn out to be equal to 1. And this is what we have discussed earlier, that you have one flavor of neutrino, and in the near detector you are observing them, or in the far detector you are observing them to be of the same flavor. This will tell you for the far detector the disappearance part, because you have a nu alpha here and you are observing the same flavor of the charged lepton, while here you have a nu alpha while you are observing a different flavor of the charged lepton. Therefore, the above figure is for the disappearance experiment, and below figure is for the appearance experiment. Or you can say that if it is a near detector, we are observing just how many nu alpha has got produced, and here we have the longer length where the neutrinos have to travel, and then we are saying that how many electron type neutrinos are getting produced in a beam of nu mu. Now, since oscillation is a quantum mechanical formula and we are generalizing the scenario, therefore I am using the evolution equation of quantum mechanics, that is nothing but time dependent Schrodinger equation. And remember, this is given by IH cross delta psi by delta t is equal to h psi, and h, since we are working in natural units, therefore h cross is equal to 1. That is why I am writing it as I delta nu alpha t by delta t is equal to s nu alpha t. Then we are saying that the for the evolution of states in vacuum, we have free Hamiltonian, and its solution will be nu alpha t is equal to e power minus iet nu alpha t equal to 0. Because we are saying that the potential is 0, therefore we have just e power minus iet, where nu alpha t or nu alpha 0 is the state at the initial time t equal to 0. Remember that if we start with nu mu, then we are talking about time t equal to 0, and therefore the thing is that at that point you have nu 1, that was cos theta nu mu plus sin theta or minus sin theta nu e. This, for a pure neutrino beam at time equal to 0, we wrote nu 1 0 as just cos theta nu mu 0. The same we are applying here. If we are saying here, just I have changed the scenario, I am talking about we have an electron type neutrino, and that is traveling in space, and therefore we are saying that now to start with, if we have a nu e beam, nu alpha 0 will be nu alpha t equal to 0, and that is nothing but nu e. And therefore the evolution for a flavor state at time t is at for any other time t, this is given by e power minus iegt u alpha j nu j. And then let us say that a neutrino of generation alpha after a time interval t is given by the eigenstate nu alpha t, such that this is equal to u alpha j nu jt, which we have written. This is given by this expression. This is just the generalization of what we have discussed in the previous class, as well as to start with in the today's class. Therefore, we have this expression uh, and then you notice the important point that this expression of nu alpha t we can obtain to get the amplitude, because we had started with t, time t equal to 0, and now we are talking about a time t, and these are orthogonal states. Therefore we are getting a delta alpha beta and this expression. And therefore when we talk about the probability, that will be the amplitude square. That means we have to talk about this part mod square. Therefore this is the case which we did on the last turn, and now we are generalizing it by taking a general unitary matrix U. Therefore nu alpha to nu beta for any time t is given by this expression, while if you see here, this is what we are doing for nu alpha that remains nu alpha. The probability is given by this expression, and nu alpha that changes to nu beta. See here, instead of m alpha alpha, now we have alpha beta, and that is why you have a beta over here. Now similarly, if you talk about anti-neutrinos, you will have a similar expression like this, and you can see that if we write the similar expression, probability of oscillation of nu L bar to nu beta bar will be the same as probability of oscillation for nu alpha to nu beta. Therefore it is nu E bar to nu mu bar probability would be the same as the probability of oscillation for nu E to nu mu, if we assume that Cp conservation holds good. Now what we did, we said that neutrinos are relativistic particle and they have got definite energy regardless of what nu one we are talking about, and therefore since here in this case we are writing it as p1 square plus m1 square. That means we are assuming these neutrinos to have definite energy. Recall in the last class we assumed that it has got a definite momentum and we wrote E1 and E2. Today what we are saying that either it can have a definite energy or it can have a definite momenta. It will have different masses, and therefore Pj, we are again making the approximation that since neutrinos are relativistic particle, this is a small number, we are expanding it, and then when we expand it, we find the amplitude to have this form as we did yesterday. And if we do that, since what we are saying that for highly relativistic neutrinos, E is almost equal to P. The propagation amplitudes in both the cases are approximately equal. That is why we say that either we are talking in terms of the definite energy eigenstates or we are talking about in terms of the definite momentum states. Thus, it does not matter whether the neutrino was created with a definite momentum or it was created with a definite energy. This is an important catch which one has to take into account while obtaining the expression for the probability of transformation of neutrino of one flavor to another. And therefore, when we are talking about the probability of transformation from nu E to nu mu, you see you are doing the mod square, and then this J is running from 1 to 2 in the two flavor neutrino oscillation case, and you see the thing which we did, cos 4 theta plus sin 4 theta plus cos squared theta sin squared theta interference term. Now for a general case, we are writing it as UE1 square u mu 1 plus UE2 square u mu 2 mod square, and then the interference term. Therefore, they notice that here you have UE1, UE2 star, u mu 1 star, u mu 2. And that is why you are getting these terms here and these terms here. And you see here in the yesterday's case, it was m2 square t by 2p, and this was m1 square t by 2p. Today we took definite energy states, and that is why here we are writing it as m2 square t by 2e, and m1 square t by 2e. Just we are combining these two expressions, and we are writing this as again as probability of transformation from nu e to nu mu, again as this simple expression. That means this is the appearance probability if you are saying that a nu e to nu mu transformation is taking place. Therefore, this is the general expression which we had obtained earlier just by considering the matrix to be cos theta sin theta and minus sin theta cos theta. Now we are generalizing it, and because why we are doing that, because then it will be easier for us to do the algebra for in three flavor neutrino oscillation case. Let us stop here. Thank you very much and see you in the next class.